Hello, everyone. My name is Michaela Bracken, and I'm a senior chemistry major. And today I'm going to be sharing with you some of my current research. I will be talking about the synthesis of fluorinated fatty acids and their use in their characterization of iron nanoparticles, and specifically iron oxide nanoparticles. So a little bit of background on these particles. They are made up of iron, oxygen, and hydrogen, and the typical oxidation state is iron 3+. These molecules come in aggregate together, and then they form clusters, which these clusters can then be reacted to form nanoparticles. And these nanoparticles have a lot of applications in the biology field and biomedical field. Some of the typical iron oxide nanoparticles are hematite and goethite, and then also magnetite. And the challenge is when these particles come together, they don't always form a uniform nanoparticles with the next nanoparticle. Whenever they're not uniform, they are called polydisperse, and the aim is to make them monodisperse, which is very uniform particles throughout. And whenever you have this uniformity, you can have the applications are easier to be applied to different fields. And so the challenge is making them monodisperse, and that is kind of what I aim to do in this project. Some of the applications that are not characterized very well at the moment, and they're still in the early stages of clinical investigation. These iron oxide nanoparticles can be used as MRI contrast agents, and they can be administered to patients. And whenever the scans are done, they make things more visible and easier to read. They also are used in drug delivery, and they can help in reducing drug concentrations, which is useful. And then also they can be used as therapy agents. If you look to the right, you can see an example of an iron oxide nanoparticle, which is ferritin. And ferritin is actually a protein storage and release molecule. And you can see the blue and the purple here. Those are the proteins, and then inside of the protein there is the iron, and a protein molecule can hold up to 4,500 high spin iron centers, which makes it a great molecule for transportation through the body. And this is just kind of an aside, not really what my research is about, but it's something that most people are familiar with and has great application in the biomedical world, and just something that can kind of wrap it together. So I will also reference this in the future, so feel free to remember it. But going forward, my research stemmed from an article that was read. My lab deals with paramagnetic metals and fluorine NMR in characterizing them. So my lab decided to look at this specific article, which was molecular level understanding of continuous growth from iron oxide clusters and iron oxide nanoparticles. And the article talked about using basic iron carboxylates as precursors for nanoparticles, and using different precursors and surface ligands in the synthesis of these. So if we look at panel A there, you can see the entire basic iron carboxylate. The gray represents the ligand, and different ligands can be used, which will be seen in this project. And then at the center, which you can go to panel B to look at here, you can see the blue iron, and then also the red oxygen. And this is a snapshot of the center of this cluster. So A shows the cluster, and B shows the center of it. With that oxygen in the center, it bridges the irons. And then you can start to see the gray there, which is the ligand. And specifically in this article, it talked about the ligand being oleic acid. It's a long fatty acid tail, which made a good protecting group, kind of like ferritin. Panel C shows the solvent decanol coming in, and when these clusters are heated, decanol can come in and form an esterification reaction and create deco-oleate, which removes the oleic acid and kind of exposes this iron oxygen center. And then whenever this happens a lot, some of the centers can come together and aggregate and form these iron nanoparticles. So what the aim of this project will be doing is making these clusters, these basic iron carboxylates, in order to be used and characterized in the formation of iron oxide nanoparticle aggregation. And so if you go to panel D down here, we can see the mechanism of this growth. It's called a continuous growth mechanism. The article presented this, and they did a really good job of forming these clusters, but they kind of presented this mechanism as more of a theory. And our aim in this project is to expand on this theory and see if it can actually be done and test this mechanism. So the continuous growth, I guess, mechanism, the theory behind it is that it gradually, the particles are gradually aggregated together and the clusters are gradually added on, so that it kind of forms a linear regression here, where it shows this linear form, and then you end with an iron oxide nanoparticle up here with kind of surrounded with all of these oleic acid greasy tails. And going forward, you will see that we kind of try to mimic this. So another member of my lab, Julia Costa, started with this. She started with the ligand of fluorofluorobenzoate because it is commercially available and it has a fluorine on it. And fluorine NMR is the main source of our research, and using fluorine as a marker and to tell what's happening at the iron center, because this is the end that will react to form those clusters. So having a fluorine on the ligand whenever run through fluorine NMR will show us how, I guess, the two will react, which is very useful, and that is the basis of my lab's research. And so here is a fluorine NMR spectra where you can see it's many spectra stacked on top of each other, and it's shown in a time sequence. So the first one is at 1 hour. This is all under heat, so it is continually reacting as shown in the article. The second one is at 2 hours, and then 4 hours, and then 8 hours. This peak corresponds with the ligand itself, and then the peaks on the left here show the whole cluster. And so this is a picture of the cluster with the 4-fluorobenzoate attached to the iron with the oxygen in the middle, very similar to what we just saw, and it shows this crystal structure. So the difference between this and the article is that it does not show that long fatty acid chain, which is what we wanted. This was kind of like a test to see if the aggregation of this cluster would work, and it did. So we will use the chemistry that Julia used to make this cluster, but using a different ligand instead of 4-fluorobenzoate. This is where my research comes in. And it's going to be a long fatty acid chain, but with also a fluorine on it. So moving on, I wanted to synthesize sodium 12-fluorostearate, which we can see down here at the bottom as the final product. It has the fluorine molecule at the 12th carbon, and as you can see, it's a long greasy chain. So to start off, I used hydroxystearic acid and took it through a three-mechanism reaction, or three-step reaction in order to come up with the final product. We did an esterification and a methyl protecting group, and then fluorinated the OH group here, and then finally removed the protecting group, and it was able to create a cluster. So I will take you briefly through the reaction of this. The first step, like I said, was an esterification. It added the methyl group here, and it was able to be successfully done. And I know that this was successful because we did proton NMR, and at around 3.6 ppms, we were able to see a nice methyl peak here that indicated that the reaction had come to completion and that the carboxylic acid was no longer there. And so the first step was successful. And so moving on to the second step, which was a little trickier, which was fluorinating this molecule. We used Extol-Fluor-E as a fluorinating agent, and the mechanism was derived from an article that I cited here. And the mechanism is not super well known, but we know it mimics an SN2 reaction with a secondary alcohol here, and to create the fluorinated product. But along with a secondary alcohol substitution, there also is some E2 products as well. And these are the two alkene products that also came from this reaction. And then also there's a little bit of starting material left over. So we had a whole mix of products here, which isn't great. So in order to separate these, I did some post chemistry on it. But before that, I was able to see the ratio of the alkenes to the fluorinated products. And using proton NMR again here, we were able to look at the the ratio of the two. The peak on the left here in the box shows the alkene at about 3.376 ppms, and then the two peaks at 4.5 and 4.3 on the right here. And although it looks like two peaks, it's actually one peak with just a super shallow or super broad splitting from the fluorine and the hydrogen coupling. So the peaks that are represented by the one is from the fluorinated product, and then the other one is the alkene product. And this was a 0.5 to 1 ratio, alkene to fluorinated product ratio, which was the best ratio that we had seen. I used several different reactants in order to do this, and besides extofluorine, and this was the best one that yielded the best products, the best ratio of the two. And so we stuck with this one and wanted to isolate the fluorinated product alone. So that leads us into the next step. So the fluorinated product also contains some starting material, and I used TLC in order to separate the two. And as you can see here in lane 2, this is just the starting material with the 12-hydroxy stearate, and that had the OH group instead of the fluorine group. And so that was just the starting material, and this is the crude product in lane 1. And as you can see, A and B correspond to the starting material, and C is the fluorinated product. So we wanted to remove A and B and just keep C. And to do that, I used column chromatography with a 3-centimeter column, and I used a 6% ethyl acetate solvent in order to isolate spots 4 through 9 and to get the fluorinated product alone. Going off that, we could tell that this was made and ran NMR on it again. So brings us to the next step. The last step is the hydrolysis step. It removes the methyl protecting group, and it added the sodium salt on the end there, which was useful in creating the basic iron carboxylate cluster. And so this was the last step, and we could tell that it was successful because the methyl peak at 3.6 was no longer there, indicated by the asterisks here. It's there very minimally, but it still was useful in this. And so the reaction ended with the final product being made successfully, and it was tested. And so finally, what was done was this final product as the ligand, similar to the oleic acid in the beginning, was used and reacted with ferric nitrate with iron to create the cluster. And so as you can see, looking at the fluorine, so this is fluorine NMR right now, because we have the fluorine molecule on it finally. And we're only expecting one peak because there's only one fluorine, which makes it useful rather than doing hydrogen with all of the different hydrogens that would be present in this molecule. The ligand by itself is shown on the bottom spectrum here, and it has one shallow or one kind of broad peak. And you can see it's at negative 181 ppms. And then when you react it with the ferric nitrite to create the complex, which may or may not have worked, we can see that it shows a super broad peak, which iron tends to do that to broaden the peaks at negative 180.7. So maybe some people might say, oh, that's a significant shift from 181 to 180. So the reaction worked. But in this case, it did not, because the ligand was successful in that it was synthesized correctly and was able to be made, but the shift was not large enough in order to tell if it actually created a complex or not. Referencing Julia's work back in the beginning, whenever she created her ligand by itself and then complexed it, the shift was much greater, in around 30 to 40 ppms difference in shift. Here, we're only seeing around a 1 ppm shift, which indicates that the sensitivity of this molecule is not high enough in order to be used in cluster formation. And that all stems from the position of the F. And so here it is at the 12th carbon, which is pretty far from the chemistry site, where the iron will be reacting from is on the end here. And in Julia's molecule with a 4-fluorobenzoate, it was at the 4th or 5th carbon and much closer to the carboxylate center. And that was the ideal position. We kind of expected this when going into this, that the fluorine was going to be too far away, but our starting product was commercially available. The 12 hydroxystearic acid. That was commercially available and easy to kind of do a trial run and work out the chemistry on this. So going forward, we are going to try to move the fluorine to a closer carbon in order to get it closer to the carboxylate center and make the sensitivity greater, so that when reacted with iron, we'll see a greater shift, and then it'll be able to be characterized that way. So ligand number 2 is what I'm currently working on. Like I said, here's the final the final ligand that we're trying to make. It's 6-hydroxy heptadecanoic acid, where the fluorine is on the a closer carbon to the end here, and it starts with something that is also commercially available as bromovaleric acid. It goes through a multiple step reaction, which creates a oxaxylane protecting group, which then the molecules then formed into a Grignard and then reacted over here. And then the same chemistry is used on the second half of the scheme, whereas we fluorinate it and then remove the protecting group and finally add the sodium salt to create the ligand, but with the fluorine with a little bit more sensitivity. So this is currently in progress and will be carried out in the future, and hopefully will be yield a better fluorine NMR with a larger shift from the ligand by itself to the ligand complex. Kind of just to wrap up and conclude this presentation, we were using iron oxide. In order to characterize the clusters and iron oxide nanoparticles, long fatty acid ligands must be used, and these ligands must contain a fluorine marker, which is really important, and the distance is very important of this. You can see as in ligand 1, 12-fluoro, the sodium 12-fluorostearate, the ligand, how far away it is, and compared to the second ligand that was just proposed. It doesn't work if it's super close or super far away. So finding the optimal distance to create that sensitivity is what we're aiming to do. And so that is what will lead into the future research. Yeah, that is all. I would like to make some acknowledgements. I would like to thank my research professor and mentor and advisor, Will Kerber, for his presence and help throughout this project. I would also like to thank another member of the Kerber group, Julia Costa, who was my lab mate, who did some preluding research for this. And then also I'd like to thank the Bucknell University Chemistry Department for providing the materials and things needed to make this project happen, as well as Doug Collins for the review of this presentation and also mentorship. And lastly, I would like to say a huge thank you to the Project for Undergraduate Research, the PUR grant, for giving me this opportunity and funding and allowing me to stay over the summer and continue the research that I have done here at Bucknell. It's been a great opportunity, and I thank you for that. So yes, thank you for watching, and I hope you enjoyed this presentation.